Section 5.2, friction. So as we continue, we're talking about forces again. And we did in 5.1, we just talked about forces in multiple directions. Well, friction is always forces in multiple directions because whenever you're going in one direction, you have friction usually resisting you in the opposite direction. So we've talked about all types of forces so far. We've talked about spring force. We've talked about the force of gravity. We've talked about the normal force. We've talked about the spring force. I just want to review real quick. If I have a box sitting here, I have two forces acting on it sideways. I have the force downward. Right? I have the force downward, which is the force of gravity. And then remember, I have the force upward, which is the normal force. The normal force is always equal to the force of gravity because the object's not sinking into the floor. So keep that in mind. Now I also have, let's say I'm pushing the box to the left. What I will now have in play is to the right, I will have the force of friction resisting me. Now, anytime I am moving a box, accelerating a box, I have to overcome the force of friction to actually begin to move that box. So that's something to keep in mind. Now, we talk about friction. There are really two types of friction. Right? There is static friction and kinetic friction. And kinetic is just the physics scientific word for moving. So anytime something moves, it means kinetic. If you're a kinesiologist, you are studying motion, how the body moves. So joints, you might study arthritis and etc. All right? Static friction is friction on the surface of objects with no motion. So regardless whether or not you're moving, there is friction there. Right? If I am laying down on a hill, a grassy hill, I'm not going to move, but there's friction, right, between me and the grassy hill. So keep that in mind. So kinetic friction and static friction. Coefficient of friction, right, with this really funky U, right, depends on the surface. So this is a number. And it varies from surface to surface, and it's just a coefficient. For example, you guys all know that ice is much slippery than sandpaper. So the coefficient for ice is really low, but the coefficient for of sandpaper is really high because that surface is very frictiony. Yeah, I'm using that word, frictiony. So what we have here is the coefficient between two surfaces. You will find on page 129 in your book explaining coefficients of friction. So something between maybe glass and wood, or wool and glass, and sandpaper and glass, and ice and metal, and anything that you're going to need for an example in questions for your questions tomorrow from the book. You're going to have to use the coefficient of friction table, which is on page 129. Now, how do we solve for the force of friction? Well, there is an actual equation. And it's essentially the same equation. For moving objects, it's force of friction kinetic, right? And it's the coefficient of kinetic friction multiplied by the normal force. And remember, as we just got done summarizing, the normal force is equal to the force of gravity. So really, you could summarize the normal force is equal to mass times gravity. Secondly, for stationary objects, same equation, except you're using the coefficient of friction for static, or something stationary, instead of the coefficient of friction for kinetic. So those are two friction equations that we throw in when we are studying the force of friction. So when we are studying the force of friction, you might get a problem like this. So you push a 25 kilogram wooden box across the floor at a constant speed of 1.0 meters per second. How much force do you exert on the box? Well, let's go ahead and look at this real quick. Let's draw a picture to help us out. Here's my box. I am pushing it this way. And so that's the force of my motion. And I'm being resisted by the force of friction. So really, I only have two forces at play here. All right. So I could say that my net force, which is the sum of all my forces, is equal to the force of motion minus the force of friction. Okay. Now let's go ahead and pull out what we need from the equation. You push a box at that has a mass of 25.0 kilograms. And the speed is a constant speed of 1.0 meters per second. Well, what that means is if I have a constant speed, my acceleration is 0. If my acceleration is 0, my net force is 0. So we can go ahead and kind of start to plug this in. So you push a 25 kilogram wooden box across the floor at a constant speed. How much force do you exert on the box? Well, we are trying to solve for the force of motion. Well, let's go ahead and do that. Just like we talked about, we have a constant speed, so our velocity is 0, so we know our net force is 0. So 0 is equal to the force of motion minus the force of friction. And we're moving the box, so we know the force of friction is equal to UK times the normal force. All right. We also know that the normal force is equal to mass times gravity. So all I'm left with doing now is plugging in some numbers. 0 is equal to the force of motion minus the coefficient of friction. Now, it's a wooden box on a wooden floor. So you're going to look on page 129 in your book, and you're going to look for the coefficient of kinetic friction for wood on wood. And when you do that, the number you get is 0.2. So we're going to go 0.2 times 25.0 times 9.8. And when we do that, we end up getting with 0 is equal to the force of motion minus 49 newtons. Which means that our force of motion has to equal 49 newtons. All right. Just like that. All right. So that's an example of force of friction. It's going to be asking for your motion, how much you push. There is no equation for how much you push because that varies time to time. Friction is a constant, so you can kind of plug in and look at how that works for friction. All right, so that's example 1. Example 2. We kind of have the same exact thing going on. So if I draw my box again, all right, on my ground, on my wooden floor, I got two things going on. I have the force of my motion, and I have the force of friction. But here's the catch. It now says, if the force that you exert on a 25 kilogram box is doubled, what is the resulting acceleration of the box? Well, let's take a look here. Let's use the same equation we had last time. We had F of net is equal to the force of motion minus the force of friction. Well, F of net now is going to be equal to, if we double our force of motion, which we just figured out in the last slide, our force of motion was 49. 49 doubled is 98 minus our force of friction. Our force of friction, nothing has changed. We're still wood on wood, and our mass of the box is still 25 kilograms. So nothing's changed, so our force of friction is going to be 49 newtons. So now we have F of net is equal to 98 minus 49. Well, we know F of net is equal to mass times acceleration. And we know that 98 minus 49 is 49. So we have mass times acceleration is equal to 49. And we can go ahead and solve for acceleration. Now that we're overcoming friction, we have acceleration. Plug in the mass, which is 25 kilograms, times acceleration is equal to 49. Do some quick algebra, divide by 25.0, divide by 25.0. And because the only number given in this problem has 3 sig figs, our answer has 3 sig figs, and our acceleration is 1.96 meters per second squared. So that is 5.2 in a nutshell. What you have to remember always is that acceleration, if there's constant speed, there's no acceleration, so there's no net force. Net force is, again, the sum of all our forces at play. And you have to think about all the forces you have at play. So we will continue with this tomorrow when you have some book problems on the force of friction. Other than that, I hope you have a good night and a great ride back from La Crescent.